So in this talk, I will talk about the OpenACC porting to GPU of the Gaia AVU-GSR parallel solver. This solver is a LSQR-based application, and the study is in perspective of pre-Exascale systems. So, okay. So during this talk, I will spend a few words about the ESA Gaia mission. Then I will explain how this solver works, and I will talk about this OpenACC porting and the successive and more optimized CUDA porting. And at last, I will draw my conclusions. So the Gaia AVU-GSR solver aims to derive the positions and the proper motions of about 10 to the 8 stars in the Milky Way, observed with the Gaia satellite with a very high accuracy in the range of 10-100 microseconds. The Gaia mission was developed by European Space Agency. It was launched in late 2013, and it was initially scheduled to last for 5 years, and then it was extended up to 2025. This last data release was published last June, and its main objectives are to make high-resolution astrometry, to map the positions and the proper motions of the stars in our galaxy, to properly investigate the origin and the evolution of the Milky Way, and to test the different theories of gravity. So to find these astrometric parameters, the solver solves a system of linear equation where the coefficient matrix is large and sparse, containing about 10 to the 11 times 5 times 10 to the 8 elements. To operate in human-sized timescales, we only consider the non-zero elements of the matrix, that is a dense matrix, reducing the problem of about 7 orders of magnitude. Also in this case, at the end of the mission, we expect a size for the matrix in the range of 10-100 terabyte, which can represent a big data problem. To solve the system, the code adopts an iterative algorithm, the LSQR, which after setting some initial conditions, it iterates the solution up to convergence, performing 2 steps, iteration per iteration. The approach 1, which iteratively updates the known terms, and the approach 2 that iteratively updates the solution. The code was initially parallelized on the CPU with a hybrid MPI plus OpenMP paradigm, where the calculation of a subset of the total number of equations, which are the observation of the stars, is assigned to a single MPI process. And within a single MPI process, the calculation is parallelized over the OpenMP threads. Besides the astrometric part, it also computes the attitude, the instrumental parts, which to find the attitude and instrumental specification of the Gaia satellite, and the global part, which compute the post-Newtonian parameter gamma. This kind of calculation requires a parallelization over many thin-like nodes, with a RAM memory between 1/4 and 1/2 of a terabyte. And this application is dominated by computation with minimal MPI communication. To run, we guarantee the maximal occupancy of the resources of each node distributed between MPI processes and OpenMP threads. And in a typical run, of a system with about 10 to the 9 of observations, which are 2 orders of magnitude smaller than the number of observations at the end of the mission, the pin iteration time is of about 4 seconds. Given that the typical number of iterations for convergence is about 150,000, we have an execution time of 1 week, which is not optimal for the future Gaia data releases. For this reason, we decided to port to GPU the code. To perform this porting, we use OpenACC. And these are the works where this porting is described. So this code runs on multiple GPUs. Here we can see a schema of the coefficient matrix parallelized on 4 nodes of a computer clusters. where the MPI processes assigned to each node are assigned to the GPU of the node in a round-robin fashion. And to run in an optimal configuration, the number of MPI processes per node has to be set to the number of GPUs of the node, since it guarantees to exploit all the GPUs of the node while maintaining minimal the number of MPI resources. This porting with OpenACC was a preliminary porting, so a first-order porting to explore the feasibility of a GPU execution of this code. Here we can see a comparison of the prod1 region for the astrometric part of the OpenMP and OpenACC codes. We can see that this structure is basically the same. In this porting, we basically replaced the OpenMP directives with the corresponding OpenACC ones. So we translated a code taught for CPU simply on the GPU by replacing these directives. And to parallelize this application, we applied a systematic methodology to parallelize scientific applications as described in these two works. The OpenACC porting of this code is the result of an online event, the Cineca GPU Hackathon 2021, where during this hackathon we had the opportunity to get familiar with the GPU programming, port to the GPU an existing application, and to get familiar with profilers. So the figure below represents the output of the NVIDIA Insight Systems profiler, which can visualize the time of the different regions of the code, execution on the GPU, data transfers from the host to the device and back, and the regions running on the CPU. We can clearly see that the blue region, so execution on GPU, is very subdominant with respect to the data transfers. So this code at the beginning of the hackathon was not optimal, was actually slower than the CPU versions, since data transfer can represent a very important bottleneck in GPU application that have to be properly managed. So at the end of the hackathon, we had a better management of the data transfers, and we managed to move the majority of this data at the beginning of the LSQR loop and to minimize the data movements per iteration. We also did a bit of rearrangement of the semantics of a prod mode 1 to improve performances, and we set a maximum number of GPU registers per thread to 32 at compile time to maximize the GPU occupancy, which results in better performances. These results can be seen again from these two profilers. Again, in this figure, we can see the NVIDIA Insight System profiler, where we can see that the GPU regions are now very dominant with respect to the data copy regions. Specifically, the GPU computation represents 70% of one LSQR step, whereas the data transfers reduces to 15%. This other profilers is instead the NVIDIA Insight Compute profiler, which shows the GPU occupancy according to a different maximum number of registers set at compile time, and we can clearly see that the 32 registers bars guarantees the maximal occupancy. We also tested the performances of the OpenMP and OpenACC codes on Marconi 100 with the 4 NVIDIA Volta V100 GPUs per node with 16 GB of memory each. We performed the 3 tests with a fixed memory on one node and with fixed memory on multiple nodes and with the memory proportional to the numbers of nodes. So in every case, the OpenACC codes is faster than the OpenMP1 with a mean gain of about 1.5, which is constant when the OpenACC code runs on the maximum number of GPUs per node. Here we can see the line of the optimal value of MPI processes for the OpenACC code. And we can also see from this plot that the weak scalability is well satisfied. After this porting, we, seeing that it was feasible to port this application on the GPU, we performed an optimized porting with CUDA, since we aimed to improve the performances also at the cost of portability. So again, we can see the comparison of the same region of code between OpenMP, OpenACC, and CUDA. We can see that in the CUDA case, the semantics of the code was deeply rearranged. The parallel region is defined in a kernel external to the main program, where this kernel is called in the main program, passing these two parameters, which defines the topology of the grid of GPU threads on which the application run, properly set to match the architecture of the GPU and the topology of the problem to solve. Again, we can see the NVIDIA Insight Systems Profiler that compares the OpenACC and the CUDA performances. In the CUDA case, the blue region running on the GPU are even more dominant compared to the other regions, and now represents more than 90% of one LSQR iteration. We also performed a better optimizations for the data copies, which were reduced. And we also ported to the GPU more regions, so the sum of data copies and CPU computation that in the OpenACC code represented the 30% of the iteration time now is reduced to 6%. So we can say that this is a compute-bound code. We again compared the performances of the OpenMP and the CUDA code on Marconi 100. This plot shows the speed up calculated as the fraction between the iteration time of the OpenMP code and the CUDA code as a function of the memory occupied by the system and of a different exploitation of the GPU resources for the CUDA code and of the CPU of the cores for the OpenMP code. So we can see that the trend of this speed up curve is increasing, and it reaches a maximum of 14 times speed up compared to the 1.5 speed up of the OpenACC code. So the iteration times passes from 4 seconds in OpenMP case to 0.3 seconds for CUDA, and the speed up can also further increase. So these are my conclusions and future projects. So we aim to successfully port the Gaia AVU-GSR pipeline on the Cineca platform Leonardo. Marconi 100 was dismissed on late July, and the porting on Leonardo would guarantee an optimal production in perspective of the future Gaia data releases. Leonardo will have actually has 4 times GPU memory per node, and the GPUs has more streaming multiprocessors compared to Marconi 100. So this means more concurrent thread and also larger performances, as some first tests already confirmed. We are also investigating a nearly equally performant but portable solution with the C++ parallel standard template library, which is object of a work already in progress and of a paper already in progress. This is also a target of a 2 years enough mini grant in collaboration with Professor Marco Aldinucci of University of Turin and of Centro Nazionale, Spoke 1 Flagship 5. To conclude, this study is also finalized to investigate the scaling properties of other applications based on LSQR, which is widely employed in HPC in several contexts, such as medicine, industry, geology, and radioastronomy, in perspective of the future infrastructures of pre-exascale or exascale. So I concluded my talk. I thank you for your attention, and I wait for your questions.